Welcome back, class. So, we've now proven that it really is true that if I make this new and exciting affine plane over a field, then any two lines with different slopes intersect at a unique point. So that was my starting point for making the projective plane over R2. And you might remember that what we're missing in order to get the property that we want, the spot it property, we need to get rid of this with different slopes business. Namely, we need to add some points to our affine space in order to make it so that, in fact, every pair of lines intersect at a unique point. So to do that, we're going to need to make what is called the projective plane. And so basically, everything I'm doing here is to just take this idea that we formalized with R2 and then reapply all of those ideas to an arbitrary field. And this idea, by the way, this method of thinking is broadly known as algebraic geometry. Basically, the idea of algebraic geometry is to say, hey, I understand the real numbers in R2 and R3 very well. I can do geometry there. And then the idea is to say, well, anything that I can describe just in terms of the normal algebraic operations, addition, multiplication, and so on, I could do over any field. So I can describe something over the reals and then translate it and then just sort of blindly follow the model over finite fields. And sometimes, like in this case, I'll get something that all works out. And so we took this whole idea of lines in R2 and we reinterpreted it to be lines in a finite field. And then we got this idea where the picture really doesn't look anything remotely like the picture that we're picturing in R2. But the theorem we want, that two lines of different slopes intersect in a unique point, still true. And by and large, that's the whole idea of algebraic geometry. So now I want to make this projective plane. So what is going to be the set of points in the projective plane? Well, we're going to start with the points of the affine plane. Okay, so this is the projective plane, which we're going to denote as P2 of F. So the points are going to be the points of A2 of F, but you probably know what's coming. We're going to add in infinity sub m for each m in F. And then we're going to add in infinity sub vert. So if f is finite, how many points are there? Well, there's size of f squared points here, there's size of f points here, and there's 1 point here. So thus, if f is finite, there are size of f squared plus size of f plus 1 points in P2 of F. Note conveniently that if the size of F is 7, 7 squared plus 7 plus 1 is 57. Our magical number, we wanted there to be 57 cards and 57 symbols in our Spot It deck, so we're in excellent shape here with this 57 appearing. Okay, for our lines, as before, we want to take our lines and we want to extend our lines from the affine plane. Namely, our pairs of lines with the same slope need a point to intersect at. So we need to add that point to each line, and we do that by inventing this fake point, infinity sub m, for two lines of slope m to meet at. And so, as before, I'm going to take this L twiddle MB, and that's going to be the LMB, the line exactly from the affine plane. And all I'm going to do is tack on an infinity sub m. Likewise, our vertical lines, I'm going to take exactly the vertical lines before, and I'm going to tack on an infinity subvert. And so, how many of these are there? There's size of f squared of these. There's size of f of these, one for each possible slope. And then remember, we need to throw in the infinity line, which I guess I will just call L infinity. And this is just going to be all of the infinities. Union, infinity subvert. And this, there's only one of these. So in total, my number of lines is size of f squared plus size of f plus 1. Again, same note. 7 squared plus 7 plus 1 is 57. So if I take f to be the field with 7 elements, I indeed get 57 total lines, like I am hoping for. Now, before, we had made note of this observation, that every line in the affine plane has exactly 7 points. Or, more generally, if I have any field, then there's exactly 1 point on every line for every element in the field in the affine plane. What did we do in the projective plane? Well, for every line, we tacked on exactly 1 point, right? I tacked on this point, and I tacked on that point, and then this new one, it also has size of f plus 1 elements. So I can go ahead and make a note, or proposition, or whatever you want. If f is finite, I guess f with bars being finite and f without bars being finite are exactly the same thing. If f is finite, then every line in P2F has exactly size of f plus 1 points on it. Okay. So, what's going on now with our spot it deck? Well, we now know what we want our lines to be. Namely, we want our lines to be these twiddle lines. So instead of taking our line from the affine plane, we're now going to work in the projective plane. And instead of L without the twiddle, we're going to put a twiddle here. And then instead of having these 7 points, we're going to just throw in, well, in this particular case, this line had slope 5, so we'll throw in infinity sub 5. And here, we'll throw in infinity subvert. And so, these new lines now have 8 points. And so these things are literally the cards and symbols of our deck. The points, including the infinity sub whatever, those are the symbols of my deck, and the lines are the cards. And so every pair, I claim, of lines, or cards, if you like, now intersect in exactly 1 point. For these two particular ones, it happens to be this 3 sub 5, which I skipped over writing here in the middle. But that is on both of them. But every pair do. And so this follows from this important theorem that if F is a field, and L1 and L2 are distinct lines in P2F, then L1 and L2 intersect at a unique point. Now, you might be fearing that there's some long proof coming, but there's not, because all I need to check, given that I know that the lines in the affine plane all intersect in a unique point, if they don't have the same slope, is that I haven't added any intersections when I went ahead and threw in this bonus point in each of the lines in the projective plane. And I need to check that every pair of lines that didn't intersect before, that is every pair of parallel lines, now intersect in a point. But I very literally just added this point for no other reason than for them to intersect there. So this theorem is basically automatic as a consequence of the theorem that we proved for the affine plane. We just took the affine plane, jazzed it up a bit, and then we're there. Also, you can prove, I won't prove this, but it's true, that every pair of distinct points in P2F lie on a unique line in P2F. Okay, so in this sense, this really is like geometry. We have pairs of points determining lines, and so on and so forth. And so then, here's the big punchline of all of this. The big punchline here is that P2 of F7 is a spotted deck. With 57 cards and 57 symbols. Okay, so let's look at this. So all of our cards, again, just to remind you, all of our cards here in a spotted deck look like this. They all have 8 symbols on them, and every pair of them intersect in one of those symbols. So these two share the ghost in common, these two share the cat in common, and these two share the hand in common. And I've just told you how to make the lines in P2F7, and so I have made here a deck of cards with it all of the lines in P2F7. And so, to start with, here is one of the lines in P2F7, and this line in P2F7 is this red line from before, where I took exactly the line 5x plus 4 and wrote down all the points. So there's 0, 4, there's 1, 2, and so on and so forth. That's all of these, except that we needed to throw in, of course, this infinity 5 to reflect that this is a line of slope 5. Likewise, this card is the blue line from before. This is y equals 2x plus 2, so there's the infinity sub 2 I had to throw in, and then there's 0, 2, and there's 1, 4, and 2, 6, and so on. And so this picture here depicts this card in red and this card in blue, and it depicts as this double circled point, the point where those two things intersect, namely the point where they both intersect is 4, 3. So if you are playing Spot It and these two cards came up, then 4, 3 is the thing that is in common to both of them. And likewise, if I turn up some additional card here from this deck of cards, then we can look and we can see, okay, this is some line. What is it that's on both of these? These two both have 5, 1 on them. These two both have 0, 2 on them. And so, if you want, I'll go ahead and deal up just 6 more of these, and you can look at the various cards that pop up. And you can find for each of these where the various intersections are. And of course, there's one card that's very, very easy to find the intersections for, namely this card. If you want to find the intersections of this card with any card, of course, you can do it immediately because you know, okay, well, that's the infinity line, and so it's going to intersect in whatever infinity. Aha, these two intersect in infinity 0. Even I can figure that one out, despite my slowness with all of these things. So at the end of the day, what this means is if you want to produce your own spot-it deck with 8 symbols per card, all you have to do is pick 57 symbols of whatever choice you want, and then come up with a bijection between those 57 symbols and these 57 symbols. That is, between the 49 regular points and then the 8 points at infinity, and then just throw them on cards in exactly this formula. And of course, in the spot-it deck, they mix up the sizes and orientation. I've sort of done that here because these show up in a random order, but basically this is the idea. So now, at the end of this, you now know how to make a spot-it deck of the regular size. And so you could make a full 57 card one and not the 55 card one that they will sell you. Also, you know, if you wanted to make a super spot-it deck, where instead of there being 8 symbols per card, if you wanted it to be really difficult, you could make there be 24 symbols per card. And then the deck could be enormous, but you could still make it so that there were 24 symbols per card, and every pair of cards in this ginormous deck would have exactly 1 symbol in common. And you can do this because 24 minus 1 is 23, and 23 is prime. Now, what you may be wondering, and what is in fact a very reasonable thing to be wondering, is what if I wanted to make an easier spot-it deck? What if I wanted to, instead of there being 8 symbols per card, what if I wanted there to only be 7 symbols per card? Well, then you run into the problem that 7 minus 1 is 6. And as we noted before, as I keep showing you, Zmod 6z is not a field. So if you attempt to mimic this construction, you will not be able to construct a spot-it deck that meets this size bound that we proved before. Their deck will necessarily be smaller. And so, in the next video, I'm going to talk a little bit more about what happens if you try and generalize this construction. What do we know? What do we not know? And it's going to turn out that we run rather rapidly into areas of math that no one knows the answers to. So we're going to talk about some open problems. But until next time, be well.